we're going to look at drawing Lewis dot structures for some more complex, a little bit more complex molecules here. So to start off, we'll look at CO2, carbon dioxide. We're following the exact same steps that we did before. So we got to look at the valence electrons for these first. We've got one carbon in here. That's one thing that's throwing a lot of people recently. We got one carbon. That one carbon has 4 valence electrons, but that doesn't mean there are 4 carbons in the compound. There's no subscript on the C in CO2, so there's just one carbon. There are 2 oxygens, and each of those oxygens is going to have 6 valence electrons. So we're going to add these up, 4 from the carbon, 2 times 6 is 12 from the oxygens. We end up with 16 valence electrons, or dots, that we can work with in drawing this structure. We got to pick a center. Carbon is part of this. If carbon is there, we're going to go with carbon. So we have carbon, 1, 2, 3, 4 dots, 4 valence electrons. And, if this is our central atom, we want to keep this in the center. So for my 2 oxygens, we're going to put those to either side. Set one here, 1, 2, 3, 4, 5, 6. Set another one here, 1, 2, 3, 4, 5, 6. So we're sharing electrons from the definition, covalent bond. We're sharing electrons, sharing between the carbon and oxygen on the right, sharing between the carbon and oxygen on the left, and we have our bonds. So let's check for an octet. Make sure we have 8 surrounding this. Let's check oxygen. We've got 1, 2, 3, 4, 5, 6, 7 with the bond. Same thing on the other side, 7 on each of the oxygens. And for the carbon, each bond counts as 2. So that's 2, 4, 5, 6 in that case. We don't have an octet. So what can happen is, notice we have these individual unpaired electrons over here. These can also share. We can share these 2 electrons between this oxygen and this carbon and form another bond between carbon and oxygen. That's allowed. We do the same thing on the other side. So these 2 electrons, they're not disappearing, but now they are part of another bond instead of being individuals. So let's pretty this up. We've got the 2 bonds between carbon and each of those oxygens. So I'm taking the exact same diagram and just making it look a little bit nicer. So in this case, we can count these up. 2, 4, 6, 8 around each. 2, 4, 6, 8 around each. 2, 4, 6, 8 around the carbon. Bonds count as 2. And we can count 2, 4, 6, 8, 10, 12, 14, 16 total electrons are in the structure, and there should be 16 there. So try one, a little more complex. H2CO, this is formaldehyde. Same basic steps, going to go a little quicker. Carbon, we have 4 valence electrons. There are 2 hydrogens in this case. Each of those is going to have 1. And then we have 1 oxygen, oxygen having 6. 4 plus 2 plus 6 is going to get you 12 valence electrons in total. Carbon is present. Carbon is still going to be in the middle. So we have carbon with its 4. And if you haven't thought about this before, I would still write it down. There are hydrogens in here. Little side note, deal with hydrogen first. All hydrogen can do is form single bonds. Let's just get those out of the way. Carbon being our central atom, those hydrogens are going to have the bond for carbon. So we got a single bond here, we got a single bond here. And now we got to deal with that oxygen. Use a different color. Doesn't matter which of these 2 you pick. Carbon is our central atom, so oxygen has to bond to it. There is our oxygen. I'll just put it down here. Doesn't matter if you put it above. And we have single bond present there. So that's all well and good. Let's check if oxygen has an octet. You got the 2 lone pairs, the 1 independent one, and then the bonds. So there's 7 right now around the oxygen, and with 2, 4, 6 from the bonds, 1 lone electron, you got 7 on the carbon as well. So like in the case of CO2, we're going to have to add an additional bond. These 2 electrons, the lone individual electrons, they are going to be shared between the carbon and the oxygen. And we can rearrange this. So make this look a little bit nicer. And there we go. So you have 8 electrons, 4 bonds around carbon, 2 bonds, 2 lone pairs, so that's 8 electrons around oxygen as well. And if you add everything up, 2, 4, 6, 8, 10, 12, we have 12 electrons, 12 dots in total in our picture. So 2 more examples. These ones are a little shorter, but things to be aware of. In either of these cases, we don't have any, there's no central atom here. We only have 2 atoms in both of these cases. So for oxygen, each oxygen has 6 dots. 2 times 6 is 12 valence electrons. Nitrogen, you have 2 nitrogens, each of which has 5. So that's going to be 10. Don't need to pick a center. There is no center here. We're just going to have 2 atoms bond to each other. Same thing with nitrogen. Nitrogen with 5 though. So there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And in both cases, we can show that single bond in between. But, like all of these examples, we've got some individuals that are going to have to pair up. So we'll do another bond here. Clean this up. 2 bonds or a double bond between the 2 oxygens. And now everything is nice and shared and we're good to go. We'll finish this up with nitrogen. We've got some lone electrons here, but that doesn't take care of all of it. We don't have an octet around either nitrogen. If you count them up, there's 7 electrons now instead of 8, but we still have these lone electrons at the bottom. Those can be shared as well. And you can have up to a triple bond. So triple bond. Otherwise, we can't go beyond that. That's too much negative charge in between there. But triple bond does work. It's been verified. Stronger than the other 2. So clean this up. We end up with N, 3 bonds, our other nitrogen, and those lone pairs at the end. And there we go. So we deal with Lewis dot structures that might be a little more complex, and we have more than just some single bonds.